Hello and welcome to Engineering Problem and Solution. Today we're going to look at the topic on the transient current analysis of RC parallel circuit. So let's draw a parallel circuit of RC which include the step voltage, and we have R here and we have capacitor here. So we'll assume that the step current with a magnitude of I naught is given as source. So we'll say this is our source here, which is I naught, and then we have the node voltage over here. We will say VT here because we're trying to find the transient analysis. So we write voltage in terms of time, and then we write this as R, and we'll say this is IR, and then we say this is IC, and this is our C. And then we also know the voltage here is going to be VR, and this is going to be VC, plus minus and plus minus. All right, let me write the plus minus like this, plus minus like this. So once we have drawn this circuit, RC circuit, which is parallel, let's consider the initial condition. So initial condition is given. We can also find the initial condition, but since this is RC circuit and the voltage across capacitor will be a short circuit initially, so V0 plus is going to be 0. So that is our initial condition, which is given, or we can find basically based on whatever the problem is. So there is a 3-step we need to follow to solve the current and the voltage. So the first step, so step one is basically we need to apply KCL at the node. Now this is what I have mentioned many times in my videos, and I will also mention this again. If you are trying to analyze the RC circuit, the first thing you need to do is, or you're trying to analyze the parallel circuit, then the first thing you need to do is to apply KCL, and KCL stand for Kirchhoff's current law. So you need to make sure that you're applying KCL, which is the first step, and state that the current going in the node is equal to current going out. So if we apply that, we can clearly see that current going in, which is I naught, is going in, and current going out, which is IR plus IC. So we can clearly see this is the expression we'll get at that node. Now since we are trying to find the current, and we need to find the node, so it's better to represent all the current in terms of node. So what we can do is, we know I naught is I naught, and we know IR is nothing but V over R. Now that V is in terms of t, so we can write VT or simply V, but let's write as VT. Now plus IC. Now whenever we are modeling the RC circuit or RL circuit or any circuit, we need to write the equation in terms of a derivative or integration. So we know, let me write this, since we know that IC is C dV C by dt. Now this VC is nothing but the voltage across the node or voltage across resistor, which is same as VT. So we're going to use that same thing. So we're going to say C dV C is become our VT over dt. So we can clearly see that there is a differential equation we already have generated here. So if we have to write in a standard format of derivative here, which is going to be dv over dt, and then we can divide both sides by r, we're going to get 1 over rc vt equals to I naught divided by c. Now this is our differential equation, first order differential equation. And this is another thing we need to keep in mind. If we are dealing with RC circuit, then we are always going to get first order differential equation. If we are dealing with RL circuit, again first order differential equation. If we are dealing with RLC circuit, then second order differential equation. So the idea is, the more the energy storing elements like inductor and capacitor you have in the circuit, higher order of differential equation you are going to get. One energy storing element in the circuit, one differential equation. If you have two capacitor in the same circuit, then you will get second order differential equation, and so on. So if you have two inductor, then so on. Yeah. So let's move on. So we'll say this is our, so this is first order differential equation for RC parallel circuit. So this is our step 1. Step 1 is done. We'll move on to step 2 now. Now in step 2, what we're going to do is, let's write this is equation 1. Step 2 is all about solving differential equation. So we'll write step 2 is to solve differential equation which we have modeled, and we can use many techniques to solve differential equation. But in this video, we're going to use Laplace, because Laplace is a modern technique and it's very easy to solve differential equation. So we're going to solve. So we're going to say solve differential equation, or differential equation using Laplace transform. Now, when we are solving differential equation, we need to look the formula because we are using Laplace. So we need to know the formulas of Laplace transform. So what are the three formulas we're going to use here? So I'm going to write those formula here. So the formula which I'm going to use are, the first formula is for derivative. So the Laplace transform of derivative is going to be SVS, because the Laplace, what it does, it converts time domain into the frequency domain, and then it provides you with the initial condition. Similarly, another formula I'm going to use, which is simply Laplace of variable. So Laplace of variable in time domain will convert into simply S domain, like that. So there is a technique. Basically, you don't need to write this as SS. You can mention this as capital letter, and the capital letter indicates is a frequency domain, which is Laplace transform after the Laplace transform, and you have a time domain which is before the Laplace transform, or we write a small letter for that. And the last Laplace transform we need is constant, because remember this side is our constant value, that I naught can be 100 or 5, whatever, and C is also a value, capacitor value, can be 5 microfarad and so on. So those things here are going to give you a constant value. So we need to know what is the Laplace of constant. So the Laplace of constant is going to be a constant over S. So those are three formula which I have to use to solve differential equation which is given in equation 1, and let's do that. So let's rewrite that differential equation. So our equation is dvt over dt plus 1 over rs times vt equals to I naught over c. And then we are going to say here is applying Laplace transform on both sides, because we can't apply just in one side, isn't it? We need to apply on both sides. So if we apply Laplace transform on both sides, we're going to write L dvt over dt plus 1 over r is constant, so we can move that outside, and then vt, Laplace of vt, and then since there is no variable here, so we need to use our constant as Laplace. So what we're going to get now? So we know that the derivative, this formula here, we can clearly see the Laplace of derivative is going to be s vs minus v0 plus. So we're going to write that s vs minus v0 plus 1 over rc, and then vs derivative Laplace of vs Laplace of vt is going to be vs. So we're going to get vs, and the Laplace of constant is going to be constant over s. Okay, now initial condition is, we need to apply the initial condition, and initial condition is 0. So if you go back to here, we can consider the initial condition is 0. So let's use that 0. Let's use different color. So we have this initial condition is 0. So what we get here is s vs plus 1 over rc times vs equals to I naught divided by c divided by s. And then we can see here that we can take a common of this and this vs. So if we take a vs common, we're going to get s plus 1 over rc, and then I naught over c divided by s. And then what we can do here is we can send this bracket, you know, this is a bracket, we can send that to the other side. And since it is a multiply here, if we send that in other side, it's going to be divide. So we're going to get vs equals to I naught divided by c divided by s, and then we can write this small bracket s plus 1 over rc. So this is what we get right now, and we stop here, and this is our going to be, let's use a different color. So this is going to be our equation 2. Now this equation 2 is our solution of transient voltage in terms of frequency domain. So this is kind of solution, but we don't want this solution. We want the solution in time domain. So what we need to do now in next step, we are going to convert this everything, whatever we have got in a frequency domain, into the time domain. So third step, so last step now, step 3. So step 3 is to apply the or we call inverse Laplace. So to apply inverse Laplace, if we apply inverse Laplace, it will convert the frequency domain, which is S domain, which you see here, into the time domain. So what we're going to say, step 3 is to apply. So we'll say apply inverse Laplace transform. So that is our step. So now again, we need a formula, because inverse Laplace also has a formula. So what are the formula we are going to use here? So here we're going to use two formulas. So let me write the formula. This is inverse Laplace formula. Okay, so the first formula, inverse Laplace formula, is 1 over s plus a. So if you have a format like 1 over s plus a can be any value, okay, like 1000, 10,000, 100 or 200, whatever. So if you have this kind of format, what is going to be your, when you apply inverse Laplace, it's going to convert that into time domain. And what is going to be in time domain is going to be exponential function with minus at. So that's how basically frequency domain is converted into time domain. So that is one thing we're going to use. There is another Laplace transform we're going to use. It is basically inverse Laplace of Vs. Inverse Laplace of Vs is going to be Vt. And then last one we need to use is constant. Remember, inverse Laplace, because constant, definitely we'll get some constant over there. So so anything as constant, constant divided by s is going to be constant. It's exactly same formula, just opposite of time domain what we did. So that's the three formula we have to use. Now pay attention here in this format, because this is the format we need to get from equation 2. And if you look equation 2, if equation 2 is something like this, including s, so we need to separate this s and this s plus 1 over rc such a way that we can apply this formula and we can apply this formula. Yeah, so we need to separate this two fraction, or this complicated fraction, or this main fraction, into two fraction between this and this. For that we are going to use partial fraction. It's very important. If you have done A level, or if you have done your bachelor, then you should know how to apply a partial fraction. Partial fraction is a technique which is going to separate a complicated fraction into two fraction, and it's a very good technique. So we are going to use that. And again, remember why we're doing that, because we need this standard, this support, basically, whatever you can say, this kind of format, and this kind of format, and then only we can apply inverse Laplace. Otherwise we can't apply inverse Laplace here to get our rigid answer. So that's why we need to apply partial fraction to separate these two denominators, and we get the answer. So yeah, so let's write the equation. So what do we have here? So equation here, Vs equals to I naught over C divided by S plus 1 over RC. So that's the equation we have here. So what is the idea here is to separate this two, which is, I would say, I don't know what I'm going to get, so I'm going to say A on the top with S plus B, which is going to be S plus 1 over RC. So if I'm able to find the value of A and I'm going to find the value of B, I can separate this complicated fraction into that fraction, and then I can apply inverse Laplace such a way that I can get my solution. So let's find the value of A and B. Now to find the value of A and B is very simple. Is what we need to do is we need to compare the coefficient of the constants and the s square and s. So how are we going to do that? So let's look at this, because we know this fraction is equal to this sum of this fraction. So let's simplify this. So if we say I naught over C is S plus 1 over RC, and then let's combine them together. Let's simplify this. So to simplify this, we know the LCM will be S times R over R times RC, and we know the A should multiply because with this value, so it's going to be S plus 1 over RC. Similarly, plus B must multiply with S. So and then we can clearly see that this thing here and this thing, they will cancel out each other. So leftover is going to be, I will say, right hand side. I will say this is my right hand side and this is my left hand side. So I will expand the left hand side now. So it's going to be, I will do that in next line, plus b times s. So let's go to the next line. I naught over c, a times s plus a times 1 over rc plus b times s. Now we can basically, now what we can do is, now we can compare. Now let's compare left hand side and right hand side. Compare left hand side and right hand side, okay, for different things. Let's compare the constant. So constant of left hand side and the constant of right hand side. So I would say here, constant, first thing we're comparing is, we know we have left hand side constant is I naught over c, and we know the right hand side we have, what do we have? We have this value is the only constant, isn't it? So we're going to get a times 1 over rc. And we can see c and c will cancel. So we got the value from here. We got the a value. So the value of a is simply what? I naught. You can see I naught multiplying with r. That is the value of a. Yeah. Similarly, again, if we compare left hand side, left hand side and right hand side coefficient of s, what are we going to get? So you can see here we have a and we have b. What about the right hand side? Right hand side has nothing. So I will say here is 0 on the left hand side, and the right hand side has a plus b. A plus b. So that means my b is minus a. Yeah, and we already get the a value, which is, so b is going to be I naught times I naught times r with negative value. So that is my b. So let's include that information which we got, the value of a and b, on this equation here. So if we include here, what we going to get then? So finally, then we know vs is nothing but I naught over c divided by s. So I'm writing the main fraction, and that is separated with a. The value of a is nothing but I naught times r divided by s, and then we got b as negative, so minus I naught times r divided by s plus 1 over rc. Yeah. Now here we can clearly see that we can apply inverse Laplace. So if you still can't see it, then what we can do is, the next line we can say, oh, my vs is nothing but I naught times r over s, whereas this I can take the constant outside and I can write 1 over s plus 1 over rc. Now you can clearly see this is formula number 1. Formula number 2 I can apply here. I'm talking about inverse Laplace. And formula number 3 I can apply here. So now let's say applying inverse Laplace transform. We will say L inverse Vs equals to L inverse constant over S minus, let's throw that constant outside and let's apply inverse 1 over S plus 1 over RC. Yeah, now we can clearly see this is our formula number 1. Let me show you that. Where is our formula? Here we go. Formula number 1. We'll get that. Formula number 2. This is here. So we'll get Vt in terms of time domain, which is a transient voltage. And then this is constant over S is going to be simply constant, which is this. So what we're going to get here is this is Vt. We'll get Vt equals to I naught times R minus I naught times R, and then exponential form of E minus 1 over RC T, because our A is nothing but 1 over RC. So furthermore, I can take Vt and then take common of I naught times R, and I'll get 1 minus E minus 1 over RC times T. And that is my solution of voltage. That is my solution of voltage. So I will say solution of node voltage. However, what we want now is we want the current. We want the current equation. So remember current equation, if I talk about the current or transient current, you can write transient current here. Current. So there are two current basically. Okay. What are the current we are looking at here? Current, transient current through, you can say transient current through resistor, which is nothing but IR. And to get IR, what we need is simply VT divided by R, isn't it? And we got the VT here. So we can say is whatever expression we got here, E minus 1 over RC T divided by R, then we can cancel this R and R. Let's use different color. Let's use white color. This and this cancel. So the transient current through resistor is simply, we can use this IT basically. Is I naught 1 minus E power minus RC times T. That is our expression here. Now last one, what about the transient current through capacitor? Let's use different color. So what about the same color? So I'm going to use the white color back. All right, so transient current through capacitor then. So what about that? We know this is IC, and the formula of IC is nothing but C dV C over dt, and we use this VC as VT. So whatever expression we got of voltage, if we do the derivative, of that, we are going to get our answer and multiply with the capacitor. So IC equals to C. What's the expression? Expression is I naught, let's use the original expression, I naught times R, and then minus I naught times R exponential minus 1 over RC T. So we know that this is constant, derivative constant is 0. We'll get the negative value definitely. So the IC equals to C is basically there, and the negative value of that, so I'm going to say multiply minus I naught R naught, which is a constant basically, I naught times R, and the derivative. So what going to happen in derivative? They simply multiply, isn't it? So whatever value we have on the exponential, is going to multiply that. So we're going to get minus 1 over RC, and exponential we're going to stay as it is, minus 1 over RCT. So minus minus, they will cancel. C and C cancel, R and R cancel. So what we get here then? We get IC equals to minus minus is going to be plus. We're going to get I naught, and everything is cancel. E power minus 1 over RC T. And that is our expression for the transient current through capacitor. And that's it for this video.